review, the rest of the notes from yesterday are kind of like a review summary, and then we're going to get into the new stuff. So the first part is just being able to do the definite integral on our calculator. Is everybody capable at this point of plugging in a function into the calculator and getting out an answer? Do we need to practice doing any more of those, or are we good?
This is for if you have the older calculator, right? Like the
Yes, the directions are like the black calculators. The process, the Math 9 is still the same, actually. It's just how you had to enter it, which is still very similar. You enter your equation. You just had to actually, like back in the day when I did it, you had to like type the equation, put a comma, put x. It didn't look like an integral. It actually looked like.
This is so much nicer because you can like literally just model it off the way it looks.
Yeah, like it looked like that. And like if you wanted to do x squared, you had to do x squared, comma. And then you had to do like x and then from 0 to 2. So like 0 to 2 is your bound, x was your dx, and like, then you got your answer. Use one of those.
Yeah, I still have a couple TIAs.
We never had to do that.
Alright, so I'm assuming then we don't need to go through these examples because we can type into a calculator. Like all of us are comfortable typing it in.
I have one question.
Yeah.
If you switch the dx and then the x, is there a critical error?
It is impossible to switch the dx and the x. Like if you have Math 9 on that calculator, you cannot move it.
Well, I mean, like, if you get the reverse number the wrong way.
I don't know what you're asking me. Have you done it on a calculator yet? Have you used one of the graphing calculators and actually done one of these?
There's a D. The D and the X always go by each other.
Push L1.
Do you always have to put an x by the d?
Yes. Or I'll tell you error.
So then why does it even ask you for a placement?
Because you could use a different variable. Like you could do alpha y and do these with y's instead of x's. I guess trying this one. Do you want to type this one in?
Today 4 plus c silver edition.
Is that pi 3?
Yeah.
Where do you put the plus 3 at the end?
Either after the dx or before the problem.
How do I put in the 3 plus 2x? Is that just
Before you would, you should have done like 3 plus 2, then done Math 9. If you did not do that, then you have to take your answer and do 3 plus 2 times and take your answer and bring it down.
I didn't get the right answer.
Is that correct?
Well, that's your integral. So you have to take that answer times 2. Because there's a 2 in front of you.
Why are you flying every?
Yeah.
Is that like an airline?
I was like,
Get out your calculator and try it.
My calculator's charging.
Here.
I know, but literally the one day I tried to charge it, it's weird. It's like wrong.
Take one of the ones that's
But it's fine. We're good. We'll figure it out. Is that like, are you being like
so this is on the graph. So I do want to actually look at this one because I think this is really cool. So what I want you to do is go to y equals.
Well, it's called branding.
So what you're going to do in y equals is type that equation in y1. So you're just typing the square root of x into y1.
It's a brand.
Okay, so now what I want you to do is you're going to hit zoom and go to 6, so it's in standard form. We've been saying that an integral is the area under the curve. So this asks us, is it 1 to 8 or 0 to 8? 1 to 8. So this asks us to find the area under the curve from 1 to 8. So what you're going to do is when you have the graph on your page, you're going to hit second trace. And do you see how option number 7 is an integral? You're going to hit enter on 7. And do you see how it asks you for the lower limit? So that's the 1. You hit enter. The upper limit is 8. You hit enter. And then it actually shows you on our graphing calculators that the area under the curve of the square root function from 1 to 8 is represented by 14.418. As I said, I want to do this one because that's pretty cool to see.
Mine doesn't go to 8 directly. It's like 8.3 something.
Is your range?
Not like scroll.
What's your
Let me
range?
look.
Not range. What's it called? X scale.
I had you hit zoom 6, so everybody's X scale should be the same.
Oh, it is.
No, I mean like
Well, I
9
go
by
trace.
1 or like 5.
So the big idea about this is if a function is continued, you're not trace. You hit second trace 7.
Oh, 7.
Yeah, 1 and then hit 8. Enter. It's not tracing. The instructions are really big.
Bomb read.
We'll take notes.
Hey,
All
I
right.
read sometimes.
I like how you say sometimes even.
Harry Potter and Michael Crichton.
Alright, so all functions can be integratable as long as they are continuous. So continuity determines integratability. Alright, so you have a given graph. And basically what we want to do is talk about that the definition of an integral is from a to b of f of x dx, where the area above is the x-axis minus the area below. So if you have the following drawing, where from here to there, the area is 3, and from here to there, the area is 7, the value of the integral would be -4. So the value of the integral from a to b of this function, f of x, would be equal to the integral from a to c of f of x dx minus the integral from c to b of f of x dx, where a to c is that 3 minus c to b, which is 7, giving you -4. Pretty cut and dry, right? Like, it makes logical sense. So if I ask you for the integral from a to c, your answer would be, if I asked you for the integral from c to b,
4, 7.
okay, could you do the integral from 0 to b? Do we know what this region is?
Yeah. Or no.
We don't, because it doesn't tell us it's symmetric. So you can't assume an area. Okay? So it says evaluate the integral using the graph and the integrand and the areas. So the value of the integral may not be the same as the value of the area. The value of the integral may not be the same as the value of the area, because the area is inherently positive, so it's kind of like speed and velocity. Speed could be positive or velocity could be negative. So you have 1/2 x minus 1. So your y-intercept is -1. Your graph goes up 1 and right 2. It also starts at -1. So what's the value when x is -1? Good. And then we have to get to 3. So we care about that region from there to there. So what two shapes do we get? Triangle. So what's the length of the triangle base here?
2.
What's the height? Okay. So the area of the triangle is 1/2 base times height. So 1/2 times 3/2 times 3 times 3 is 9/4
Negative.
for an integral.
But not the actual.
Yep, so you have to be careful. So the area is 9/4. This area here, what's the length of the base? Ooh. Yeah, it's just 1. I think I have an extra little line drawn in there. Sorry, guys. Because it only goes to 3. And then the height here. Good. So the area of the second triangle is 1/2 base times height. So the second area is 1/4. So the area of both or all curves is 9/4 plus 1/4, which is 10/4 or 5/2 or 2.5. Yes. Okay. That's what we're talking about, the difference between the two.
We're talking about
Area is inherently positive. So I'm not writing this as the integral. This is the area, hence the A. For the integral, you're exactly right. I have to incorporate a negative. So the 9/4 is a negative area because it is all below. So when I talk about the actual integral value, it would be negative 9/4 plus 1/4, which is negative 8/4 or negative 2. So the value of the integral does not have to match the value of the area.
So area is like you ignore all signs.
Area is like speed.
Okay.
It's a magnitude. It's absolute value.
And then integral you do have like signs.
Exactly.
Okay, thank you.
You're very welcome. Can the area equal the value of the integral? Yeah. Could we have manipulated this problem to be that way? How could you have changed this example so that the area and the integral were the same value? Yeah, you could have made it go up more, or we could have started at the root. So if you change the bounds of the integral to be from like 2 to 3 instead of negative 1 to 3, then if the entire value was positive, then your area and your integral would be the same. Okay? Similar example, we have a linear equation starting at a positive 3, going up 1 and over 2. Does that line ever make it below for this problem? No. This is a case where everything's above, right? So you need to know the values at -3 and the values at +3. So what shape does this create? Yep. So the height of the trapezoid is from -3 to 3, which is 6. The height of the base at 3 is like plugging 3 into your equation. So that's 3/2 plus 3, which is the same as 3/2 plus 3. 3 plus 1/2. 3 minus 3/2. 1.5. So your area is 1/2 height, B1 plus B2. So 1.5 plus 4.5 is 6. Maybe that's it. Half of 6 is 3. So you get the area is 18. We're going to start looking at something called a power rule tomorrow. So the power rule is kind of like doing a problem like this backwards. So you could find the actual. Now in this case, because it worked out nice, the actual and the area.
Madeline Smith, please come to the office.
So does the area of the integral equal the area of the actual shape? Yes. So the area and the integral have the same value in this problem, because I have no points at which the area is below the curve.
You could ask her for a pencil if you weren't going to write.
Alright. Didn't want to.
Okay? We should start to be able to look at this and kind of see what shapes we're graphing. So you have a square root of 4 minus x squared. So what shape does a square root give us? Talked about it yesterday. Michael said he's never seen it before. Yeah, it's a semicircle, right? Then it's a semicircle of what? Radius. Good. So it's a semicircle of radius 2. We know that because this is r squared minus x squared. So we have a radius of 2. So if this goes from -2 to 2, then I know that that's my radius, width, and height. But what does a -3 after a function do to our, what's that transformation? Yeah, it's going to go down 3 units. So instead of being at -2, 0, and 2, 0, these points all get shifted down 3 units. So my points go to -2, -3, and 2, -3. If the radius height is 2, that means that my y-intercept is 0, -1. So when your calculator and you find the area, we find the area between the curve and the x-axis. Whether the area between the curve and the x-axis is above or below kind of changes where we're going to find it. So you're not finding the area underneath this circle.
You do need that.
You're finding the area between the x-axis and the circle. So do you like remember the problems where you used to have circles inscribed in squares?
Yeah.
And you had to like find the area of the square, and you found the area of the circle, and then you subtracted one from the other? That was a build-up or a lead-in to integration. You just didn't know that what you were doing in geometry at the time was actually a manipulation of an integration scale. So you said it, we need that area. Why? Yeah. So what we're going to do for geometric purposes is we have to find the area of the rectangle. So the area of the rectangle, so this is from -2 to 2, good. So that means that this has a width of 4 and a height of 3, restricted down 3. So the area of the rectangle is 12, and then in order to find that shaded region, what do you have to do? I have to subtract away.
R squared.
I bet you. I have to subtract away the area of the semicircle. So the area of a half circle is 1/2 pi r squared, where in this case my r value is, or 2 squared. So
2 square root pi 2.
Therefore, the area of the light blue region what is the value of 2 pi approximately?
3.5 or 6.3.
Yeah, 6.28. 4.14 times 2.
I had 6 in my brain, but I started saying something else.
So this area is going to be close to or near what number? If it's 12 minus 6.28, like 5.72. Go ahead and use your calculators on that Math 9 feature. And if you want to watch it graph it, you can. So you could do it on y equals if you want to watch it graph it, or if you don't really, if you don't really care to see what it looks like as a graph, you could just do it in your normal mode.
What did we get?
Roughly, it's going to be smaller than it, though. I have an overestimate right now. I said 5.7.
According to this, basically looking like it's around 2 pi.
Okay, but 2 pi is 6.28. No, it should be less than that.
I put it in and it gave me 6.28.
I got 5.7, maybe. Yeah, so yeah. So if it's, that's a stupid question, but if it's under the curve.
Yeah, I got 5.716, and we wrote down 5. Wow, that's really blurry.
I'm retarded.
So the calculator gives us 5.716. So our approximation, because we approximated 2 pi, was really awesome. Hannah, you go, it's negative. Why is it negative? Everything's under the x-axis. So the area we got is 5.72. The actual value of the integral, again, in this case, is negative 5.71. I'm going to say 6, just to be. Does that make sense? Do we start to see, like, the connection? See how good you guys are at doing math? Like, look how close you were to the actual.
I didn't include the negative 3.
So this one is a lot like your homework problem that you guys asked me to do at the beginning of class, where we talked about like the line and then we plugged in the generic A's and B's. These are definite, like, AP type questions. They love general. Like, they love ones that aren't a strictly numerical answer. So for this problem, again, that represents a linear function with a slope of 3. So it's just a line with a slope of 3. It starts at A and ends at B. So it is a, yep. So the height at A is 3A, height at B is 3B. So then the area is 1/2 the base, which is B minus A, times base 1 plus base 2. So a lot of these problems end up being more algebra than anything else. How does the power rule work in Calc? So if I asked you to take the derivative of x squared, what's its derivative?
2x.
Okay. If we were to work backwards to take 2x and get it back to x squared, you're basically adding 1 to the power, right? And dividing by that power. So you add 1 to the power, divide by that power.
Is that when you have to use the variable integration or whatever?
But this one you don't, you have bounds. So what we're going to do is a little sneak peek into tomorrow. So that theta is kind of like an x. If you want to write x, that's totally fine. So the rule would be that we add 1 to its power, whatever that power is, you divide by. It's going to be exact. And then we're evaluating from B to A. So what you do is you plug in the upper bound and you subtract the lower bound. Because basically what it's going to do is if you plug in the upper bound, it calculates from 0 over. So then you subtract the lower bound to get rid of that little tiny triangle there. So it would be 3b squared over 2 minus 3a squared over 2. So these general ones with like the a's and the b's when we're doing the shapes of the figures are a preview to exactly what we're going to do tomorrow. Do you see how they're almost identical? Well, they are identical. I just wrote 1 over 1 fraction.
Yeah.
It's really cool how geometry directly relates to. This is the one time you can actually see a usefulness to what you're doing in geometry and how those shapes matter. Good? Do we need to do more like this, or are we okay from doing the homework? No, we have to do the read stuff. That's why I want to know if you're okay with this stuff. Do you understand how the integral works better? Okay, I do want to talk about that one. So I said I don't remember what this. Why is something like that not integratable? What happens at x equals 0? It's not continuous. What's the theorem we got at the beginning of class today? Continuity implies differentiability as well as now integratability. Yeah. So integration is implied by continuity. If a function is not continuous, you can't integrate it. So something like 1 over x, where you're trying to evaluate it from 0 to 1, because 0 is not a continuous point, it is not integratable. If you had changed the curve to be 1 to 2, then it is. So the bounds matter. So discontinuity matters.
This also the
Wait, I thought we said it didn't. I thought we, wait, never mind, that's differentiability, never mind. Okay.
Next one is your we could write out this whole thing, like on a test, to show that this is.
No, I'm just showing you why.
But like on a test, all we have to say is it's not continuous at 0.
I brought back differentiability. Like, I want you to understand how they relate. And then this is a limit, so again, just bringing back. What is the definition of continuity? So the definition of continuity wasn't strictly for derivatives. That's like the general definition of continuity. So you need 3 things to be continuous. Has to exist, the left-hand limit has to equal the right-hand limit, and the limit has to equal the domain value. So in the case of this problem, it fails all 3. Because 1, f of 0 is undefined. 2, the left-hand limit doesn't equal the right-hand limit. And then 3, the left-hand limit doesn't equal the right-hand limit, and it's undefined. None of the above.
I mean, if it is undefined, that means that the main value doesn't exist.
So it already quits. But the thing is just going back to the definition of continuity. And saying, okay, this is why this doesn't work. Okay, so the one thing you hit into on your homework on 5 and 6 was the Riemann sum being able to be written as a limit, and the limit being able to be written as a Riemann sum. This is something that wasn't previously hit hard on the AP test, and in the past 2 or 3 years, we've noticed an increase in a number of problems, typically, which is super frustrating. The problems appear on the calculator portion, where a calculator is utterly useless to you in this part. So, there are a couple things that we have to understand in making that connection. So, the connection or the idea is that, first off, how did we find our subintervals, or what did we define our subintervals to be? What was the delta x? What did we call delta x? Or what we refer to a lot of times as the dx of a problem. How did we find our subintervals when we first started doing Riemann sums?
With the one minus the other.
Perfect. We called it b minus a all over n. So if you look at the multiple choice answers to A, B, C, and D, do you notice how they have an n at the very end of them?
What's that?
That n at the very end is represented by b minus a over n. Where do you get the b and the a? What are those?
Upper and lower bounds.
Those are your bounds. Perfect. So in order to get the end of these multiple choice answers, you have to take the upper and lower bound, and basically we're replacing dx with that. So in the case of example 1, dx would be 5 minus 3 over n. So you get 2 over n. Getting 2 over n does what? It eliminates 2 answers. That happens every single time. Because they say a student misunderstanding is that the answer is 1 over n always. That is like that's one of the misconceptions of a student, and they pick A or C, and they don't pay attention to the rest. So, that's the first thing you want to look for. Then, just looking at the formula, what do you notice about both A, B, C, and D? They all start with a, like what's that? What's right after the summations? A 3. That 3 is representative kind of one of your bounds in a way. So when we're looking at this, what we are doing is kind of saying, okay, we know that this is raised to the power of 4. I know that b minus a is 2. And then there's this 3 kind of aspect being put into it. So that's kind of representing your lower bound in a way. So then what do you notice about what's being added? We have k over n and 2k over n. Where do you think that relationship kind of comes into play? What, in terms of the summation, is that part of the problem supposed to represent? So after the summation,
Change in height.
yeah, it's supposed to represent your height, right? So in terms of this problem, our height is x to the 4th. And it's x to the 4th at 3, and it's x to the 4th at 5. But we have that power rule to it where we're like adding and subtracting. So we know we're down to b and d. So the big difference is the k over n versus the 2k over n.
So thoughts as to why it would be one versus the other?
Yeah.
Would it be D because, like, I don't know if this is right, but hypothetically, if you had to plug in the delta x into, like, the actual equation, that would be the only one that would be, like, correct?
Yes. Yep. So the correct answer is D.
What's the reasoning again for that?
Want to say it again? You said it well. So it's if you hypothetically plugged it into your delta x, and you like worked out, it's the only one that's going to work in terms of this problem because the k over n doesn't represent that subinterval of 2.
Okay.
So example number 2 is the backwards kind of reversal of this. They give you the limit, and you have to figure out which one it could be. So we know, just based off this alone, that b minus a has to equal 1. So there's only one answer. So that 3 in that problem represents that constant of integration. So if you have a constant of integration built into your problem, so it's like 1 plus 3x, the 3 over the kn is going to represent that linear constant of integration. Okay. So the correct answer for 2 is A. So what I have is some problems again for you reviewing this aspect and reviewing Riemann and trapezoidal sums. And then that's going to pretty much summarize Riemann and trap. And then we're going to move into 5.3, which is actually finding antiderivatives using the power rule backwards tomorrow.
Now, will we take a quiz in this or just a chapter test?
I technically always have quizzes for every unit.
Well, we don't need to do that.
Do I think we need a quiz right now? Probably not. We have a decent amount of points. If you think about it, I hadn't planned on having one. And maybe we could do one on Thursday next week, so you have a 4-day weekend. So,
I'll be able to get it.
I'll be in West Virginia.
I was thinking about giving you, remember I talked about the driving project? Thinking about giving you the driving project over the 4-day weekend, because it's not a challenge, it's like,
do that instead.
it's kind of like easy points, and that's what I think I don't always assess on Remont sums, because I can give you the driving project.
Can you give it to us a little earlier?
Yeah, I can give it to you on Monday. Like I have everything ready for it. So that way, in case you go away for the holiday weekend, I'll give it out Monday, and I'll just do the following Tuesday. So I have like a week to do it outside of everything else you guys have going on. And then, so for tonight, I just want you guys to do those 2 handouts. Tomorrow, we'll go over them, especially the Remont sum handout. And we'll start anti-derivatives, which is kind of like the power role of integration. Which is interesting.